start. So good evening, everybody who are joining us from India, and good morning to all who are joining from the US. And it's very hard to mention everybody around the world. So first, let me introduce Professor Avi Loeb. And I think it is really a difficult task to give Avi's introduction because there is a risk that it might be too long. And Avi does not need any introduction to anyone who is working in the field of astrophysics and cosmology. But for everybody, just let me mention few things about Avi as a host. So Professor Abraham Loeb, Avi Loeb is a Frank B. Bart Junior Professor of Science at Harvard University. He was the chair of Department of Astronomy for almost 10 years, and he's currently acting as a director of Black Hole Initiative and Institute for Theory and Computation. He authored around 800 papers. He has contributed almost all fields in astrophysics and cosmology, from the early universe to planet formation, and also in the search for extraterrestrial life. He also authored 6 books, including the latest one named Extraterrestrial, the first sign of intelligent life beyond Earth, which is going to be released on 26th January worldwide. Now, on a personal note, I am hugely inspired by Avi's general writing. When I was feeling low and depressed a bit during my PhD life, my collaborator, Professor Girish Kulkarni at TIFR, who also worked with Avi at Harvard, suggested me to read Avi's book From the First Stars to Milkometa. I really enjoyed that book, and I have read that book probably more than 10 times. Another thing is about Avi is his quotations. I mean, unfortunately, we don't know much about when scientists give some real speeches like politicians, but I would like to mention one quotations by Avi. I was listening one interview of Avi's graduate student, Amit Siraj. Please correct me, Avi, if I misquote you. And Avi once told him that the sum of our knowledge is like a small island in a vast ocean of ignorance. So today we are very glad to have Avi Loeb among us. We'll focus both on the vast ocean of ignorance and also the island of knowledge. I'm sure we'll be enlightened today, and Avi will be the guiding star in the direction of that island. I thank Avi once again and welcome you to our forum. Just for audience that we'll have three segments basically. In first section, we would like to know more about Avi's journey as a researcher, starting from Avi's childhood. And in second section, we'll talk about Avi's new book. And in the end, we will take some questions from the audience. So let's start from the beginning.
Thank you for having me. Before you start, just wanted to thank everyone for coming, and I hope you will be inspired by what we discussed today. Go ahead.
Thank you. So the first question I would like to mention from your book that you have written that I grew up in Israel on our family's farm in Beit Hanan, a village about 15 miles south of Tel Aviv. So how was your childhood growing up in a farm in Beit Hanan, Israel? And what you wanted to be in the future at that time? Did you have any thought?
Yeah, so first I should say that I don't think I'm very different now than when I was a kid. One of my objectives in life was to maintain my childhood curiosity and to stay innocent and true, and not try to create an image of something different than I am. So anyone that knows me knows that I speak out my thoughts, and I don't do political calculations. Even though I served in leadership positions, I basically try to convey the truth. And in that sense, I'm acting like a child, because actually the Harvard Gazette, the newspaper here at Harvard, which is the official magazine, asked me, what is the one thing you would like to change about the world? Which is a big question. And I said, I would like my colleagues, all the tenured professors, to behave more like kids, because there is something to be said about not worrying about your image and taking risks and basically trying to understand the world. That's what kids do. And as scientists, we have the privilege of pursuing that and getting paid for that, which is amazing. You know, that why would people pay us to enjoy our wonder about the world? That's the privilege of being a scientist. Of course, the reason they pay is because science brings in knowledge that can be used also for practical applications, and we can see it through our technologies. But the basis of science, the roots of it, are the wonder. And when I grew up on a farm, I didn't know that I'll become a scientist. I was collecting eggs every afternoon and driving the tractor to the hills of the village where I used to read philosophy books. So I was mostly interested in philosophy because it addresses the deepest questions we have. Unfortunately, it doesn't give answers to the questions. Science, on the other hand, addresses the questions in principle that we can answer. So it's a subset. And early on, I worked in the farm, and I was thinking about becoming a philosopher. But then in Israel, you have to serve in the military at a young age, at age 18. And so I had no choice but either to run on the hills with a gun or to do intellectual work in the context of physics, which is useful for the defense of the country. So I selected doing physics. I was recruited to a program of 20 to 30 people and I finished my PhD at age 24 at the Hebrew University in Jerusalem. And also at the same time, led a project that was supported by the United States, by Star Wars. There was an initiative of Ronald Reagan in the mid-1980s. And that brought me to the US very frequently. And then in one of the visits, I went to Princeton, the Institute for Advanced Study, and eventually they offered me a 5-year fellowship under the condition that I'll switch to astrophysics. And I didn't know anything about astrophysics. I didn't know the vocabulary. It was very depressing because in the environment that I was as a postdoc after my PhD, it was very competitive, and all my cohort of people that worked around me looked down at me because I didn't really know the vocabulary. It took me time to define my projects. I had no mentor that would tell me do this or that. And then there was an opportunity at Harvard for junior faculty position, and I applied to it. And the person that was selected decided not to take it because the chance of getting tenure is very small. And I decided to accept it because I could always go back to the farm. That was plan B. And I'm still, thinking about it. It's not obvious to me that being surrounded by members of academia is so much beneficial to being embedded in nature, like I was on the farm. There is something relaxing to being with nature rather than with people. I don't like big crowds. I don't have any footprint on social media. I can tell you an anecdote. I have a class, a freshman seminar for students in their first year at Harvard. And I asked them a question. Suppose a spaceship were to land and ask you to come in. Would you do it? Would you leave everyone and just go on the ship for an adventure? And to my surprise, not to my surprise, everyone said yes, but to my surprise, almost everyone said that they will do it under one condition, that they could share the experience on social media with their friends. And I just couldn't understand it. If I were to go to the Himalayas to climb a mountain or to go on a ship like that, or I would enjoy the experience. I don't care about other people sharing it with me. That's really irrelevant. So to me, it's a foreign culture, all these social media. I don't, and it saves me time. And also it allows me to think independently in a way. So that's how I ended at Harvard doing astrophysics. And eventually I realized that even though it was an arranged marriage to astrophysics because of circumstances, it's actually a marriage to my true love, because there are many philosophical questions that astrophysics addresses, such as how did the universe start? Where did we come from? Is there life elsewhere? Are we the smartest kid on the block, of the galaxy? all kinds of very deep questions that we can address nowadays with scientific instruments. And that's very exciting. Yes, we can.
Yes. Hi, I'm a graduate student at Raman Research Institute in India. So I would like to know more about your years in the military service. Like when you look back now, do you think that it helped you in some ways, or do you think that it was a waste of time?
Well, interesting question, because when I was in the military, I actually served in a research center, which is similar to a national laboratory in the United States. And it's a different culture than academia. I mean, I also had a military service per se, where we went to all the military sections in order to see what it is like to be a soldier. So I parachuted, I drove tanks, I did a lot of things that just to get to know what a soldier does. And by the way, one thing I learned is that this statement that sometimes a soldier has to put his body on the barbed wire in order for others to cross over. And the statement among soldiers that sometimes a soldier needs to put his body on the barbed wire to allow others to step over. I have a sense now when my book comes out that there is a lot of pushback against the proposal that I make in the book. But I feel that it's important to allow the younger generation of tomorrow to be able to speak freely on the subject of the search for technological signatures of other civilizations. But coming back to your question, I was at a national research center similar to the national laboratories. And there is a different culture there than in academia, where there is a higher purpose that people work for, and it's not so much about their ego. In academia, professors, when they get tenured, often build an echo chamber around themselves with students and postdocs that repeat the theme of their research and repeat their mantras, such that their voice will get louder in the community. And then they improve their chances of getting awards, honors, and so forth. So that is part of the academic activity, but it's not as much in the context of these national laboratories, where there is a bigger goal in the mind of people, which is to help the security of the country. So in that sense, I actually miss those days when I was surrounded by people that worked together collaboratively. It was less about the individual ego of each person promoting himself or herself, which is very common in academia. And one of the items that I discuss in the book actually is, this is my second message in the book, that physics is a dialogue with nature, and it's about us learning from nature, from experiments. And then it's not a monologue where we are trying to do intellectual gymnastics and impress other people that we are smart. Physicists working on a subject that has no connection to experiments, and a completely theoretical construct, like, for example, extra dimensions or string theory or the multiverse. And these are ideas that may be fascinating intellectually, but may have nothing to do with reality. It reminds me of some of the work done by the ancient Greek philosophers. So, for example, Aristotle argued that we are at the center of the universe, that there are spheres around us. And of course, that is very appealing to people, to think that we play a central role in the universe. And there was this beautiful mathematical picture of the motion of the spheres and so forth. And it turned out for 1,000 years, people believed Aristotle, but then Copernicus and Galileo demonstrated that it looks like the Earth is moving around the sun. We cannot be at the center, not even of the solar system, not to speak about the fact that later on it was discovered that the sun moves around the center of the galaxy, and then the galaxy is one out of 1 trillion other galaxies in the universe. So clearly, we are not at the center of the action. So what I'm trying to illustrate with this example is that sometimes you have a beautiful idea, and it could be very mathematically sophisticated, but nature is something else. And if you want to understand nature, then it's not about showing off that you are smart. It's about getting feedback from experiments and that guide you in the right direction. And that is one of the issues that I discuss throughout the book.
Okay. So now just I would like to focus on your new book. So could you please tell me that what is your new book all about and why we should be interested to read it? And I have read it and I enjoyed thoroughly, but for our audience that what it is all about.
The book is primarily about an object that was discovered in 2017 called Oumuamua. It was found by a telescope in Hawaii on Mount Haleakala called the Pan-STARRS. And that telescope was tasked in finding all the near-Earth objects that endanger us, that are bigger than 140 meters in size. As you know, the dinosaurs were killed by a big rock, roughly the length of Manhattan, the island of Manhattan, tens of kilometers in size. And we are smarter than the dinosaurs. We have astronomers that can warn us about a rock approaching us. It must have been a beautiful sight for the dinosaurs to see this rock getting bigger and bigger on the sky. And the fun stopped when it hit the ground and created the Chicxulub crater. So NASA was tasked by the Congress in the United States to find 90% of all the objects bigger than 140 meters. And the first step in that process was done by Pan-STARRS. And the next step will be done by a telescope called the Vera Rubin Observatory in 3 years. So while surveying the sky, Pan-STARRS discovered the first object near the Earth that came from outside the solar system. And the name that was given to it, Oumuamua, represents scout in the Hawaiian language, or a visitor from far away. And this object, at first, astronomers thought, okay, well, it's interstellar, therefore it was ejected from another planetary system around another star, and it must be a rock, just like all the objects we have seen within the solar system that are debris left over from the formation of the planets. And most of the rocks in the solar system are in the outer Oort cloud, in the periphery of the solar system, and that is the reason they appear as comets, because these rocks are covered with ice. So when they get close to the sun, the ice evaporates and creates this cometary tail, a trail of gas lagging behind the object, the core. So they said, okay, well, it probably is a comet that originated from another star. And the only problem was that there was no cometary tail. And in fact, the Spitzer Space Telescope looked very deeply at this object and didn't see any trace of carbon-based molecules or dust around it. So it was clearly not a comet. And so people said, okay, well, maybe it's an asteroid, a rock. But it turns out that it exhibited an extra push away from the sun beyond the force of gravity. And the question was, what gives it this extra push? Because if there is no cometary tail, there is no rocket effect to give it the extra push. If the extra push that was detected was from a cometary tail, the object needed to lose about 1/10 of its mass, at 10%, which is a large fraction. It's not small. And then also this object was exhibiting, as it was tumbling, spinning around, the amount of light that was reflected from it, sunlight, changed by a factor of 10, which means that the object has an extreme geometry. Because even if you imagine a piece of paper tumbling in the wind, it's very unlikely for it to be exactly edge on. And a factor of 10 means that it's quite extreme in it's at least 10 times longer than it is wide projected on the sky. But then the best fit to the light curve was that of a flat object, disc-shaped, not a elongated object like you have seen in cartoons. It was more like pancake than a cigar-shaped object. So that was very puzzling. We've never seen anything like it before. And my main concern was, what is giving it this extra push? And the only thing I could think of is the reflection of sunlight. And in order for that to be effective, the object needs to be extremely thin. about 1 millimeter, because you need the surface to mass ratio of the object to be large, so that the reflection of sunlight gives it enough push. And that resembles a sail that you find on a boat, and except that instead of being pushed by the wind, here the sail is being pushed by light, by reflecting light, sunlight. And this is called the light sail. And in fact, our civilization is currently developing this technology for space exploration, because the advantage is the spacecraft doesn't need to carry the fuel with it. The other thing I should mention is that in September 2020, just a few months ago, there was another object discovered which exhibited also an extra push by reflecting sunlight, and did not have a cometary tail. And so the Minor Planet Center at Harvard gave it the name 2020 SO, an astronomical name, because initially it was not clear what it is. But then extrapolating the orbit back in time, it was clear that it came from the Earth. And indeed, there was a mission in 1966 called the Lunar Lander Surveyor 2, and the rocket booster was kicked into space from that mission. And that must be the rocket booster based on its orbit. But because it was hollow and thin, the reflection of sunlight caused a deviation in its orbit. And we know that this object was artificially made by us. We don't know who made Oumuamua. And that is the discussion that I have in the book. So one aspect, the main, I would say the main core of the book is about Oumuamua and what implications it might have for our civilization. And the second is about the scientific culture, which is not ready to accept any discussion at this time about the search for technological signatures. And I find that inappropriate, because about half of all the sun-like stars, based on the Kepler satellite data, have a planet of the size of the Earth, roughly at the same separation, meaning that the planet could have liquid water on the surface and the chemistry of life as we know it. So what we find in our backyard, not only that we are not at the center of the universe, but moreover, the things we find around us, like the Earth-Sun system, is very common. There are billions of such systems in the Milky Way galaxy alone. And then there are 1 trillion galaxies like the Milky Way in the entire observable volume of the universe. So that means, to me at least, that we should adopt a sense of modesty. We should not assume that we are special and unique and that we are the only ones, but instead, the most conservative assumption is to say, under similar circumstances, you end up getting the same outcome. And therefore, we must represent the typical conditions that you get in all these planets. And therefore, we should just search for either primitive life or intelligent life. These are the two forms that we can imagine based on what we see here on Earth. And unfortunately, this doesn't sound speculative to me, but for some reason, the mainstream in astronomy does not think that way. And I think the mainstream is wrong about it, because we can search for technological signatures with the same telescopes. For example, the astronomy community is now planning the next generation of telescopes to look for oxygen in the atmospheres of planets around other stars. And oxygen, turns out, will not be conclusive evidence for life, because in the first 2 billion years, the Earth didn't have much oxygen in the atmosphere. So if you don't find oxygen, it doesn't mean that life is not there. The Earth had a lot of microbes, but the oxygen level was not high in the first half of its life. And on the other hand, even if you find oxygen, it doesn't necessarily imply the existence of life, because you can get oxygen from natural processes, chemical processes, for example, the breakup of water molecules or other things. And so people will debate forever whether the detection of oxygen or even methane is indeed evidence for life. However, if we find industrial pollution in the atmosphere of another planet, like the CFC molecules, complex molecules that we produce with our industries or refrigerating systems, then it would be conclusive evidence for life, because nature does not produce such complex molecules. So with the same instruments, you can look for oxygen or you can look for industrial pollution. But the astronomy community, even though I wrote a paper about industrial pollution just 5 years ago, the astronomy community will not motivate these future observatories based on the search for technological signature, because it's considered in the periphery of the field. It's considered something that we should not speak about, that there should be a taboo. It's not being funded much at the moment, and young people are discouraged from working on it. And so to me, it looks just like stepping on the grass and saying, look, the grass doesn't grow. Obviously, if you don't fund effort in that direction, we will not find anything. And the real crime here, I would say, is that the public is extremely interested in this subject. This is a subject that fascinates young people, fascinates the public at large, and the public funds science. So how can the scientists say, no, we don't want to discuss this question, even though we have the instruments to address it? I find that to be unacceptable. And that's the second message that I have in my book.
Don't you think that it is becoming like a religion, like you want to believe in it or you don't want to believe in it?
Well, it
like
should not
in
be,
scientific community, it should not be, but
it
it
should
is
not
divided.
be. Let me give you an example. In the Middle Ages, some people thought that dissecting the human body should not be done, because the human body has a soul, it has some magical powers, you're not supposed to get into it, okay? And imagine what modern medicine would be if we didn't have operations, okay? And if the scientific community would say, oh, there is all this nonsense being said about the human body, we don't believe this nonsense, therefore we don't want to examine this question at all. That makes no sense. If you find some nonsense, let's say in science fiction literature or in people that report about unidentified flying objects, that has nothing to do with what the scientific community can do. You know, the scientific community can use the telescopes we have, the instruments we have, to address this subject scientifically, just like the medical community addressed operation of the human body scientifically, even though there were claims that didn't make much sense on the same subject. And I think partly it's because the scientific community wants to remove itself, to put itself on a pedestal, removed from the public. It sounds like this is too much of interest and therefore we should have a taboo about it. I don't think that way. I think the dialogue with the public is a good one, and it could help to fund science. And in fact, scientists have an obligation to attend to the interest of the public.
Thank you, Avi, for explaining it. It's really nice to hear that the edges of scientific community, like how it is divided, and being a young researcher, I'm very happy to know about it. So what I want to ask now that, for example, like what are the next steps for this search of extraterrestrial life? For example, if we see that Oumuamua is related to any interstellar civilization, then what scientific community should do to advance these searches? On the other hand, if we find it is just an ordinary comet, do you think it will be an obstacle in the search for this extraterrestrial life?
Well, it's not possible for us to get more data on Oumuamua because it's now 1,000,000 times fainter than it was when it was close to us. It went too far out and we can't monitor it anymore. And unfortunately, when we could do it, the astronomy community did not collect as much data as it should have. And we discovered it on its way out, so we didn't have the opportunity to follow it. What we should do in the future is find other objects that look similar, that are strange and have these unusual properties. And in fact, the Vera Rubin Observatory has a good chance of finding one per month. There is no good reason to assume that Oumuamua was the only one, because we looked at the sky just for a few years and we found it, and with the sensitivity of Pan-STARRS. And that means that if Pan-STARRS continues to look for another few years, it will find another one. We don't, I mean, again, it's the Copernican principle that says we are not at a privileged place or a privileged time. So otherwise, the probability for finding it would have been extremely small. If only in a window of 3 years out of the age of the solar system you could see such an object, that means that it's extremely unlikely that we would have found it.
Ronita, please go ahead.
Is it a good idea to look at moon, because moon doesn't have any atmosphere, and if such a particle comes, and then it will not be destroyed by the atmosphere?
Yeah, so that's an excellent question. And the moon is sort of like a museum. The Earth has an atmosphere, and an asteroid or a comet that collide with the Earth burn up in the atmosphere. Unless they are big enough. So if they are bigger than a few meters, then the core of the object remains and gets to the ground. But the smaller objects get burned up, and they are called meteors. And in the moon, you don't have an atmosphere, and therefore it collects all the objects that collide with it, including the small ones. Another advantage of the moon is that it doesn't have geological activity. So on the Earth, within 100 million years, the surface layer of the Earth gets mixed up with the inner region of the Earth by geological activity. So if there was a civilization on our planet with computer monitors and other things more than 100 million years ago, we would never know. You cannot have an archaeological dig deep into the core of the Earth, and so it's impossible to find out. And on the other hand, the moon collected everything that collided with it. It's sort of like a museum. The only thing that happened is you have these impacts all the time. So there is a layer of about a few meters in depth where collisions so created dust out of the rock. But it would be very interesting if we go back to the moon to regard it as an archaeological site, in the sense of searching for what collided with it. And some of the objects that impacted on the moon could have been from interstellar origin. So if there are artificial objects that are not natural in origin, we could find the debris over there.
Okay. Do we have any estimate of the mass of this particle, Oumuamua?
We don't know the mass, but we know roughly the dimensions, because the Spitzer Space Telescope tried to detect the heat coming from it. And we know the trajectory, so we know what the surface temperature of the object was based on the trajectory, how much it was heated by the sun. And the fact that the Spitzer Space Telescope could not detect the heat coming off it gave an upper limit on the size, which is of order 100, 200 meters. And then we have a lower limit on the size of order 20 meters if the reflectivity was 100%. So if it was like a mirror reflecting sunlight, then it must have been at least 20 meters in size. So we know that it's between 20 meters and of order 100 meters, roughly the size of a football field. So therefore also the reflectance from it could be somewhere between 100% and maybe 5%, a few percent. We don't know. But other than that, we don't have a good idea, because we didn't have a photograph of the object. So all we know is that it's most likely at the 90% level, more likely to be disc-shaped, flat, like pancake, rather than cigar-shaped.
Spherical.
Yeah.
Okay, so just coming back to your book, so I want to just talk about another topic. So could you please tell us more about the Star Chiefs project, and when we can expect its launching, and how we can trace its progress in our lifetime, and what are the opportunities it will bring to young researchers?
Right. So the Starshot project was defined or announced publicly in 2016, and the goal is to visit the nearest star, which is Proxima Centauri, and it is 4 light years away. So it takes light 4 years to traverse that distance. And the goal of the project was to visit that star within 20 years, within our lifetime. And the question is, how can you do that? I mean, the only way is to have a spacecraft that moves at a fifth of the speed of light. And I was given the opportunity to lead the advisory committee that would try to find which technology would be the best to use. So together with my students and postdocs, for 6 months, we looked at all possible technologies. And the only one that seemed feasible is the light sail technology that I was mentioning before, where you have a lightweight sail that is roughly the size of a person, very thin, of order a micron thickness, that weighs about a gram, and is being pushed by a very powerful laser beam, about 100 gigawatt, that is focused on that sail. And then you can show that within a few minutes of acceleration by the laser beam, you can get to a fifth of the speed of light with this sail. And the sail can carry electronics. It can carry a camera, navigation device, communication device, and then be launched to a target where it will take photographs and communicate back. So for example, Proxima Centauri has a planet in the habitable zone around it, and we would like to take a photograph to know whether it's a desert, whether it's yellow, or maybe it is it has oceans, blue, or maybe it's green, and or red, or whatever. And we would like to get a color image of that planet by flying close to it. But also there are many other targets of interest, even within the solar system. And so we announced the project, and Yuri Milner, an entrepreneur from Silicon Valley, committed to fund it. He was involved in the planning, of course, and he was the one to ask me to come up with a method that we can use for that purpose. And right now we are pursuing 3 technological challenges. One is the photon engine, this laser beam, how to make it from many small lasers. The second one is the light sail, the sail itself, to make it lightweight and also made of material that is strong and highly reflective, so that, because if it absorbs more than 10 to the minus 5 of the laser beam energy, it will burn up. So a challenge is to make the sail. And then there is the communication between a very distant probe and us, which is very challenging. And that is the third big challenge that we are addressing. There are groups of people thinking about these different challenges right now, and they are being funded.
Okay. What kind of material are you thinking about?
Oh, so that's to be determined. There are some papers on that. And just to give you an example, diamond is an excellent material for that purpose. It turns out it's very strong, and it's highly reflective. And maybe we will end up using a diamond in the sky. You know?
So I don't want to keep I don't want to keep it going for a long time, because we asked Avi for 1 hour. But Avi, if you are available for around 20 minutes or something like that, we can take questions from the audience.
Well, maybe 10 minutes. I can accommodate 10 minutes.
Okay. So let's go quickly. I don't want to keep you.
Yeah, go ahead.
So let me just talk quickly. So these are the general questions. So how will the universe end? It is asked by Shreya Datta from Calcutta University and Devashish Mukherjee from Ramakrishna Mission Vidya Mandir, Belur.
Right. So the end of the universe, I mean, the future of the universe depends on the constituents of the universe. And we measure them right now at the present time. And if we were to use the standard cosmological model that we have, which is based on a cosmological constant that dominates most of the mass budget of the universe. It's about 70% today at present of the mass budget. plus matter plus radiation, if we extrapolate this simple model that we have into the future, what we find is that all the sources of light that we see in the universe outside of our galaxy, that we know that they are receding away from us. But in fact, they will continue to recede away from us faster and faster as time goes on. So the universe is accelerating, and we would lose them because eventually they will move faster than light relative to us. So they will exit from our horizon in a finite time in the future. So if you imagine this accelerated expansion of the universe continuing, then once the universe ages by a factor of 10 or so, all the galaxies, all the sources of light that we see outside of our galaxy will exit from our horizon, and the only sources we could see would be within our galaxy. And that is a gloomy future for astronomers, because it means that extragalactic astronomy will not be possible. There will be a darkness surrounding our galaxy. Now, of course, stars like the sun, they have a finite lifetime of about the age of the universe today. But stars that are like Proxima Centauri, or even slightly smaller, that are most of the stars, they are dwarf stars, they can, about 10% of the mass of the sun, they can live for trillions of years. So about hundreds of times more than the age of the universe today. So you can imagine having those stars that are around us continuing to shine for trillions of years, which is 100 times the present age of the universe. And eventually they will also die. And the question is, what will happen after that? Now, it's possible that when civilizations will be trillion years old, they will develop some means of maintaining themselves. They will not need, obviously, stars to warm them up. Currently, we rely on the sun, but you can imagine that in much less than a trillion years, in maybe even thousands of years, we will develop the means of a sustainable habitat that we can send to space, and without any need for a star next to you. I mean, if it's based on nuclear energy, for example. I mean, a star is also a nuclear reactor. You know, there is nothing to a star other than gravity holding it together. And so we can imagine creating something like the space station, a platform in space that will be self-sufficient and will not need a star. You know, that. But it's something for us to think about. We will have a lot of time to think about this. The sun will burn up, will boil off all the oceans on Earth within a billion years. We will have to move out of the Earth. Definitely, for sure, no doubt about it. Irrespective of what we do with the climate, we will have to move out within a billion years.
Okay, so I want to ask one general question, which is asked by Sandeep Kumar Kataria from Indian Institute of Astrophysics, Bangalore. So he asked that as a young researcher, I would like to ask, how do you choose a particular problem in which field you would like to contribute? How do you choose a particular problem?
Yeah, so it really depends. I think the first criterion to use would be a problem that excites you, that you're not just doing a calculation because it's fashionable or because someone else told you to do it, but because the subject that you're working on is exciting, it's interesting for you. That's the most important aspect. And then there is another consideration of how risky this subject is. In other words, if you work on it, it's possible that you will end up at a dead end and nothing interesting will come out of it. So I think early in your career, you want to work on less risky topics because you have to establish yourself. You don't want to take too much risk because if the project ends up not successful, you lose it. So you should be more strict about selecting topics that are not, that are likely to give you results no matter what early on. But once you become a professor and you have tenure and you don't have to prove yourself anymore, Then, of course, the advantage of tenure is you can take risks because you will not lose your job. Unfortunately, most of the professors that when they get tenure, they do exactly the opposite. They become even more conservative because they want to preserve their image and they want not to make mistakes and they want not to take risks and just, you know, keep boosting up their image and ego and so forth. And that's unfortunate because it's they're not taking advantage of this great privilege of tenure that gives you the freedom of your research so that you can go in directions that that otherwise you would be worried about whether they would lead to the right results. And you know that Einstein himself made 3 mistakes at the end of his career, and it's making mistakes is part of the process when you work at the frontier, when you take risks.
Yes, thank you. Yeah, Radhika.
There is a question from Pratik Taraftar. Pratik, will you please go ahead?
Hello, Professor Loeb. The concern which you raised regarding the faculty members who have to keep up with their image, that is very true, and I think it's a generic concern right now globally. And also the dearth of funds, the issue regarding the dearth of fundings, which you said. So that is also a very generic issue globally right now. I have a question. I was wondering, I don't know, maybe it might be a wild goose chase, but when we are looking for alternate civilizations or maybe life on other planets, to be more specific, then we usually look for habitable regions in other stellar systems. So when we say these habitable regions or habitable zones, then usually we assume that the form of life which we are speaking about, which we are looking for, is the form of life as we know it on Earth. So are the astronomers thinking about alternate forms of life? I don't know. Maybe it's a very difficult question to answer because we really don't know what other forms of life can there be. But have the astronomers given this point a thought?
This is an excellent question. I should mention before I address your question that I also have a textbook that we completed with a former postdoc of mine, Manasvi Lingam. He's originally from India. It's 870 pages long, and it will come out with Harvard University Press in June on June 25th, 2021. So in about 6 months. And this would be a scientific textbook that gives the full background on what life is and how to search for it, both primitive life and intelligent life. And we hope that this book will lay the foundation for future research. So if you wanted to learn everything that we know, then look out for this book. It's called Life in the Cosmos. It already has a web page, and then when it comes out, you might enjoy the science behind this search. But to answer your question, it's a very good question. What we can imagine is based on our experience, right? We cannot imagine something that we have not seen, and nature may be much more imaginative. And in fact, you could have different types of liquids that support life, not just water. It could be ammonia or some other liquids, and it was not explored much in the literature. There is a paper by Carl Sagan about possibility of life in ammonia. One way to address this question is in the laboratory, and I have a colleague of mine at Harvard, Jack Szostak, a Nobel laureate, that is trying to produce synthetic life in the laboratory. And one can imagine also doing experiments, not just producing a synthetic cell in the laboratory, but also trying to play with different fluids and seeing, under which circumstances chemistry of life can come to exist. And that will improve our imagination. So I think one way to improve our ability to forecast where life may be found is by doing experiments that expand our experience, And so you raised a very important question of the possibility of life that is different than the one we know. And I think the way to make progress on that would be to do laboratory experiments on life that looks different than what we know.
Okay, thank you, Professor Loeb. Now I will end up with the last question by our one of our organizers, Sovika. So Sovik, go ahead.
Uh, yeah. Hi, Professor Loeb. I have a question that is, uh, hello?
Yeah, we can hear you. Go ahead.
We
Yeah.
can hear you. Go
So
ahead.
I have a question that is slightly different from the main topic today about life outside Earth. So I was recently reading a paper of yours on curvature tension with, I think, Sunny. And so I have a question regarding this both. I mean, what is your opinion on this curvature tension right now, and also the Hubble tension crisis?
Right. So with respect to the Hubble tension, I'm not. I'll tell you my problem with um, its its existence. The problem that I have is I don't see a simple theoretical explanation for it. All the attempts that were made to explain it, they came up with rather complicated and fine-tuned models, and so to me it's not an appealing situation. If if there is no simple explanation to such a tension, perhaps it's the observers, the people that use type 1a supernova have some systematic error in the way they analyze their data, and that they are not aware of at that level of a few percent. That's quite possible, and we have to find it. Now, the microwave background physics is really simple, and it's hard to believe that anything is wrong there. What I would consider is that something is wrong with what we are doing at low redshifts, and one way to figure it out is by using a method that is relying again on simple physics. And the method that I favor the most is gravitational wave sirens. So we have only one event for which it was used, and already it was constraining quite nicely the Hubble parameter, but hopefully we'll get more. And I think that will resolve the matter. If we get more neutron star mergers, then that we can have a redshift from the electromagnetic counterpart and then measure the angular diameter distance from, or luminosity distance from, the gravitational wave signal. That would be the cleanest way, but also using other methods. And there is this tip of the red giant branch that Wendy Friedman is examining, and she gets something sort of in between. And I think one has to wait a little, because if she gets something in between, then maybe and obviously Adam Rees wants to get a second Nobel Prize, right? So we have to wait and see how it goes. So I wouldn't yet declare that there is a real that we are confident in the tension, because also it would be really difficult to explain it. All the models are rather convoluted. And with respect to the curvature, I would say the same thing. I think the standard model does pretty well, and the deviation from it is not robust at the moment. So I think curvature is very likely to be zero, the way that the microwave background originally argued, some 2 decades ago. That's my guess.
Yeah. So just one other thing, that the standard sided measurement is basically cosmological model independent, right?
Sorry, sorry, which one?
The standard sided measurement from gravitational waves is
no. It's cosmology independent only if the source is at very low redshift. But if you put the source at a redshift 1/2 or 1, then yes. If it's at low redshift, you only measure the Hubble constant. It's not you don't measure the density parameter. But if you find sources at redshift above 0.1, then you can start to constrain also the other cosmological parameters.
Okay.
Yeah.
Okay. Okay. So thank you very much, Abhi. I just forgot to do one thing. So I didn't get a chance to introduce ourselves actually. So within just 1 minute, I would like to introduce all our organizers with you.
Yes.
So I am Anirban Roy. I am a postdoc at Cornell University working with Professor Nick Batalia. And I'm working on cosmic microwave background anisotropies, particularly secondary anisotropies, and also working with few experiments like CCAT Prime, Simon Observatory, and CMBS4. Now, Arnav and Avinash and Souvik, could you please introduce yourself quickly so that we come to
Hi,
the
I am
center?
Arnav. Uh, I am final year PhD student at IIT Indore in India, and I work with UGMRT dataset to understand the post-UR H1 signal or to detect the H1 power spectrum mostly. Thanks.
Thank you.
Avinash?
Hello, Abhi. My name is Avinash, and I'm currently a final year PhD student at IIT Kharagpur. And I work with Professor Somnath Bharadwaj, and I do mainly simulations of the EOR signal and some predictions of uh, with the current configuration of SK low. And yeah, so
Very nice.
thank you. Thank you
Yeah.
for the
Shobhita?
discussion. Yes.
Yeah.
Last.
So I am Shovik Roy Chaudhary. I'm a postdoctoral fellow at IIT Bombay, and I work with Vikram Rentala here at IIT Bombay, and also with Steen Hannested in Aarhus University in Denmark. So I mostly work in neutrino cosmology.
Yes, and the background behind you looks like San Francisco.
Yeah, actually. So that is one of the it's just the laziness of using one of the
I have changed it actually for Avi. It is pale blue dot here. I
Okay.
cannot point it out.
And
So thank you very much,
Yeah.
Avi. We are out of time. And sorry for the initial disturbance. I am really sad and I
Wait,
apologize for all of you.
did Ranita say she didn't say?
Okay. Yeah.
Oh yeah, I
Oh, Ronita
introduced.
didn't know. So sorry, I forget.
Yeah,
So
go
I
ahead.
introduced myself earlier. So I'm a PhD student at Raman Research Institute, Bangalore in India. I work with Professor Biman Nath, and we study the interactions between the galaxies and intergalactic medium, mainly focusing on the cosmic rays.
Oh, okay. Very nice. It's very nice to meet all of you. And once the
Yeah.
pandemic is over, come and visit us at Harvard. If you want to give a seminar. For now, the campus is closed until
Yes.
at least until July. So, and that was one reason that I could finish my book so efficiently because I had much more free time.
Yeah.
Thank you.
Okay.
Very nice
Thank
to
you
meet
very
all of
much.
you. Okay.
Yeah. Good
And
luck with your new book.
Yes.
Thank you. Thank you.
Thank you.
If any of you are interested, there are a number of podcasts that came out. One was with Joe Rogan and another one with Lex Friedman. And there was also a review of my book in The New Yorker. So you can find all of these and get more insight about the content of the book.
Okay.
Sure. Thank you very much, Avi.
Yeah.
Bye-bye.
Thank
Have a
you
good
for
day.
giving us time. Yeah. Bye.
Nice